Okay, so this time we are interested in looking at another common alkene reaction, which is halogenation, which proceeds through a bridge. So let's look at the mechanism for that. So let's say we have this molecule on the left, and we react it in the presence of Cl2 in the solvent of CCl4. So CCl4, just like last time, is just a solvent. It's not going to play a role in the reaction. Okay. So just like last time, when we were looking at hydrohalogenation, start by once again redrawing the reagents and the original molecule that you have, and identifying once again what the nucleophile and the electrophile are. So since we're again doing alkene reactions in general, we're going to look at the double bond as nucleophilic and whatever else is left as the electrophile. So once again, we're going to have the movement of the electrons from this pi bond to the ClCl. Okay, so there's one important thing to know about this. It's that as this ClCl gets closer and closer to the pi bond, because these are the same atom, you get an induced dipole across it. So as this negative approaches this species, what you have happen is this turns into a partial positive, and this turns into a partial negative. Okay. The next thing that happens is that, well, let me write that down first. So again, the XX bond, in this case that could be ClCl, BrBr, or II, is polarized by the pi bond. Okay, once that has happened, just like last time, we have the attack of the nucleophilic pi bond onto the ClCl. And just like last time, this bond breaks. Now it's a little less obvious why this bond breaks this time. Last time we said that the hydrogen couldn't have two bonds to it, so this bond broke. Just know that the movement of electrons from here onto the Cl also breaks this bond. What happens in addition to that, though, is a little bit strange, and it's the difference between the carbocation intermediate and this intermediate. So not only does an arrow originate at the pi bond and go onto the Cl, but the Cl has a lone pair that goes back and attaches to the pi bond. And what you have looks kind of strange. It is this species here. So again, let's first look at this. So this bond breaks. The electrons from this bond move on to the Cl, which is now negative, and this other one now has one arrow going to it and one arrow going back, so it attaches to both the carbons that were previously involved in the pi bond. And because it now has two bonds to it, it has a formally positive charge. The other way you can figure this out is that, remember, our charge always needs to be conserved, so this species turns negative. Since this on the left hand side is a net neutral, this on the right hand side also needs to be net neutral. So if we generated a negative charge, we also need to account for that by making a positive charge. Okay, so you'll notice that both these are wedges. So what we could also have is both of these be dashes. So what exactly is going on here? Well, the ClCl approaches from either the top or the bottom, and when this bridge forms, this we're referring to, this halonium ion intermediate, it can either attach above or below. To better look at this, I've recreated this structure in Chem 3D. Hopefully you can see most of it, but over here is our original molecule, and this is the 3D image of it. So you'll notice that this bridge over here is pointed upward in space. Okay, so what else happens? Well, now that this bridge has formed, it is open to attack by the remaining Cl ion. That's going to look like this. So the other Cl, which is now negatively charged, is the most nucleophilic thing currently here. So this is our nucleophile, and now this is our electrophile. So this now attacks the bridged complex. Now there's two subtle points about this. The first is that you'll notice that when the Cl attacks, well, it's going to attack from the bottom, and the final product will look like this. Perhaps I'm getting a little bit ahead of myself. But as it comes from the other side, this bond now breaks, because remember, now we have 1, 2, 3, 4 bonds to carbon as this forms. And, well, we'll technically have 5. So 1, the bond formed here, 2, 3, 4, and 5. So you know one of these bonds must break. And it's going to be this other bond that's attached to the bridge. What you're going to get is one of the CLs on the bottom and the other CL on the top. Now let's go back to this diagram over here. So what we're saying is the other CL is coming and attacking at the bottom here. So you'll see that in space, this CL is negatively charged, yes? And the Cl anion that we're saying is a nucleophile is negatively charged. So all around the top of this bridge here is going to be negatively charged, which means that the Cl anion cannot approach from the top. What it needs to do is it needs to go around to the bottom and attack it at the back. Okay, but wait, there's a little bit more. So which side is it going to attack? Is it going to attack the left, more substituted carbon, or the right, less substituted carbon? Well, we've already sort of shown what's going to happen here. And this is also a little bit of a subtle point. So if we look closer at the intermediate that's formed, if, say, we had a Br-Br complex, we would have, well, the attachment of this, the halonium ion that we're seeing here, and then we have this sort of intermediate. So pretend you don't see anything else other than the complex formed from, say, this. Okay? So you can't say these are in equilibrium, because again they don't have the same bonding makeup, but you could say these are in, well, again, you can't say they're resonance structures, but they are in equilibrium. So the reason why this bridge forms is that, unlike H, which got attacked before and formed the carbocation, the Br is attaching, and it still has a lone pair that can reattach to this carbocation immediately. So this is so fast that it is almost concerted. But you can say that these species, the halonium ion bridge, which is what we're talking about, and this carbocation here, are sort of in equilibrium. So the equilibrium will favor the more stable carbocation, even if it never in reality actually forms. So at the tertiary location right over here, that creates the more favorable carbocation than at the secondary. But again, we can't call it a carbocation because that species actually doesn't exist. So what instead we say is that at the more substituted location, that has a larger positive charge, and at the less substituted, that has a negative charge. Well, technically it also has a del plus, but we'll say that this more substituted side has a partial positive charge, and that electronically attracts the Cl minus. So here you're seeing a conflict between sterics and electronics, and in this case the electronic argument wins. The negative charge is more attracted to the positive charge than the problem that there's bulky groups there that makes it difficult for the Cl to get in. So again, the electronic argument wins. The resulting fact is that this Cl on the bridge stays on the top and the other Cl attacks on the bottom, and it attacks on the more substituted side. What the resulting, I guess, product demonstrates is what we call, well, okay, again, the attack occurs in the more substituted carbon, but this has anti or trans, maybe not geometry, but stereochemistry. Okay, so if that was a lot of information, I'm going to sum it up right now. So bridge intermediate is formed due to lone pair on X. That's one important thing. The bridge forms on one side, either top or bottom, which we represent as either wedge or dash. The attack occurs at more subbed carbon because of that partial positive that we're saying is sort of there because of the carbocation that doesn't actually exist but sort of exists. Kind of weird like that. And lastly, final product has anti stereochemistry or trans. That is to say, when we're looking at the groups that added both these CLs, they are on opposite sides of the molecule. Okay? So again, there's a lot of ideas there, but it'll become more obvious in a few more examples. So the one good part about these bridge intermediates is that they're a lot less complicated than the carbocations, because there are no rearrangements that could really occur. Okay, so let's look at another reaction. And again, this time the reactants will be slightly different. Instead of using the CCl4 solvent, we'll be using H2O as the solvent, and you'll see how this changes the reaction. So once again, what will occur is that as the Br-Br complex approaches, again we see this double bond here of the alkene as our nucleophile and this Br-Br complex as our electrophile. The double bond will come out and attack the Br, which is polarized once again. So this will have the partial positive, this will have the partial negative, and the lone pair on this Br will simultaneously reattach at one of these carbons that are on the double bond. Once again, the halonium ion intermediate is what you get. In this case, just to show that it's completely arbitrary if you choose top attack or bottom attack, I'll say that they're both on a wedge. So the bridge is formed by a wedge, so it attacked from the bottom. Okay, and we have this Br anion remaining. Okay, so what's the tricky part? Well, this time we're working in water instead of CCl4, so as you might have guessed, the water will actually play an important role in the reactivity of what goes on here. So here we have two things present. We have H2O present in much excess, and we have the Br anion that was formed from the first step of the reaction. What I'm going to tell you is that the H2O is the better nucleophile. There will probably be a video later on that tells you how to determine what the better nucleophile is, but the other argument you can make is that the H2O is in excess. So there's a lot more H2O molecules than there are Br minus. Right? So the H2O is much more likely to attack than the Br. And as we were saying before, how do you decide which side it attacks? Well, this is a secondary carbon, and this is a tertiary carbon. So since we have a stronger partial positive at the tertiary carbon, what happens is the H2O will attack there. And subsequently, you will generate this. Remember, the O is still attached to two H's, so now we have a positive charge here. Again, net charge was conserved. The halonium bridge is always positive. We had that negative counter ion, and now once again, our net charge is +1 -1, and over here it is again +1 -1, so charge is conserved. You probably recognize what to do with this from doing a lot of the carbocation intermediate examples. What we need to do is a deprotonation here to make the alcohol. Also notice that since this bridge was on dash, what happens is this attacks from the other side, so the water molecule is on a wedge and the Br is on a dash. Again, we call this anti. And anti sort of refers to the attack, whereas trans refers to the fact they're on different sides. Okay? So here we have two options. The first option is that for the deprotonation, we use the Br anion, which is sort of hanging around, and it takes the H off. And again, because we formed two bonds to H, one of them needs to break. That's going to be this one, and that electrons in that sigma bond are going to go onto the oxygen. And what results is our final product, which looks like this. So again, the Br added first, it was in the bridge on the dash, and the OH added on the other side. So a requirement of these bridge reactions is that you get a trans product as far as whatever adds. Again, referred to as anti during the attack. Okay, but we do have sort of a problem here. So you'll notice the counter ion formed in this reaction is HBr. So what do you know about HBr? Well, you know that HBr is a strong acid, right? And in general chemistry, they taught you that the conjugate base of HBr is Br minus. So if this is an incredibly strong acid, that means that Br- is an incredibly weak base. So really we've written a reaction that should not go to completion. This has a terrible equilibrium constant, because again we're going from a weak base to a very strong acid. So is there a better base that is present in this reaction? In other words, while we have the right product, it is very unlikely that we have the right counter ion. Okay, well, the other thing that was in there is the solvent, which is in excess. So if we have water do the deprotonation instead of Br-, what we will get is the same product, but a different counter ion. So we'll have the hydronium hanging out here, and we'll still have the Br- hanging around here. I should probably make sure, just for consistency, to include the Br- over here, because remember, once again, charge is conserved. If we have a net neutral over here, a minus and a plus, we also need to have a minus and a plus over here. Okay, so the other thing to note is that, once again, the bridge that we formed in this step could have been a wedge-wedge, in which case the water would have added on a dash. So this can be the enantiomer, and you'll get them in equal proportions, which will give you a racemic product. Okay? Alright, one more that's sort of unique we'll take a look at. Okay, so suppose we have this sort of problem. We have X2, and in this case we have alcohol. Now, if you remember from our carbocation problems, you might already have figured out what the major difference will be here, and it's not too surprising. So again, I don't know, I have the Br2 here. Let me check. Okay, looks like I didn't actually copy this problem down, so let me swap it out for another one. We'll leave this as an exercise to the end. Okay, so say we have this problem instead. Again, we're adding an X2 and we're adding an alcohol. Okay? So the first step, once again, is the polarization of this Cl-Cl bond and the addition that occurs. And so again, the nucleophile attacks the Cl, it breaks this bond. At the same time, the Cl comes back and attacks. Again, we result in a bridge that can either be wedge-wedge or dash-dash. And that's going to look something like this. Once again, we have the currents that we compare our nucleophiles. We see that we have a Cl- and we have an alcohol, and the alcohol is actually the stronger nucleophile. So the alcohol will participate in the attack. Once again, we need to look at the positions that could attack. This is a secondary carbon, and this is a tertiary carbon. Because this has a stronger partial positive, it has a stronger hypothetical carbocation, the attack will occur at the tertiary. And finally, you will generate this as your product. Okay? And of course, you can also have the enantiomer if the bridge formed on the opposite side. And, well, okay, I guess I spoke too soon. You still have this oxygen positively charged, and you have an excess of ethanol. So what you can do is the common series of deprotonation steps that you most often do. And that will get you to this product, the enantiomer, and these two counterions. Okay, since I somehow lost the solution to that problem, we'll do one more. And this one you will try on your own. So let's take a look at this. Okay, so everything that you need to know to solve this problem has been shown to you, so take a few minutes, pause the video, and try to solve it yourself. Alright, let's give it a try. So again, the first thing that happens is that the I2 complex or molecule approaches the double bond, is polarized, nucleophile attacks, this bond breaks, I goes back and forms the bridge, which will look like this. Okay? And remember, depending on whether you form this bridge as wedge-wedge, everything that was attached there needs to move back. So these are pushed down in space to wedges. Okay, this is actually symmetrical, so it doesn't matter which side your nucleophile attacks, but remember, again, this time you're doing it in water. Water is a better nucleophile, so it'll attack from the bottom side at either of these locations. It doesn't matter because it's symmetrical, and you will get this. And once again, since your solvent is water, you can do the series of deprotonation steps that are required to get to your final product, which will look like this. And of course, the enantiomer. There are counter ions. At this point, you should be able to figure out what those are on your own. Let me see if I have any problems. Actually, seems like I do have a solution to this one. Maybe. Yeah, maybe. Okay. Well, give it a try yourself. Take a few minutes, and then I'll show you the answer. Alright, I'm going to assume that you tried it, sort of gave it away, but the attack will happen like this. I just rotated the molecule. That doesn't matter so much. Once again, you get the formation of the bridge like this. I arbitrarily chose wedge-wedge to form that halonium ion bridge. And this time, since you're doing it in CCl, CH2, Cl2 doesn't play a role. So the strongest nucleophile you have is the Br. Again, this problem is symmetric, so you don't have to worry about which side it attacks. And your final product will look like this. Again, note that the Brs are on opposite sides of the molecule. Okay, so in summary, what we looked at today was these three reactions. So your halogenation, which is the transformation of an alkene to a halide, what is called halohydrin, which is the reaction of an alkene and the halide, an alkene to make a halide / an alcohol. Again, here we had the addition of X2 in some solvent like CH2Cl2 or CCl4. We formed a bridge. There's no Markovnikov's rule to worry about here because, well, it's the same thing. It's a Cl and a Cl, so there's really no difference. And the addition is trans, or again, many people refer to it as anti. Over here in the halohydrin formation, that was the second reaction we're looking at. That's X2, which is again some sort of halide. The solvent is water, which is a stronger nucleophile than the X- anion. So it'll perform the attack, giving you a halide from the initial step and an alcohol from the attack on the bridge. And it's technically Markovnikov because the more electronegative group adds to the more substituted carbon. And lastly, we looked at haloether formation, which again had X2 as the major reagent, and the solvent in this case was some sort of alcohol. So it was just like the halohydrin formation in that the halide forms the bridge, and then the alcohol attacks the more substituted carbon to give your final product, which again must have trans or anti-stereochemistry. Alright, hopefully that made sense. Good luck.